Good morning, this is Dr. Kumar Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain Newtonian fluid flow in a circular tube. So the flow is being considered fully developed laminar flow in a pipe. So pipe is given by this, so this of the radius r. These are the directions of theta, so of coordinates actually. So z direction is taken along the axis of the pipe. Theta, you can see the movement from here to this side, and r is only in the direction of the radius, and velocity vector is always perpendicular to the r. So this is how you have this side. So this is the differential r, and we can calculate in order to calculate the volumetric flow rate. So the length of the pipe is L, and pressure applied at entrance is P1, pressure at point 2 is P2. So we can calculate here del P upon del Z term here. So we can integrate it for the entire distance. So it will come here P2 minus P1 upon Z2 minus Z1. So from here del P upon del Z is minus delta P by L. So this is how it can be calculated. Z is acting in downward directions actually. So now consider the flow through horizontal tubes and all this. Now we are putting continuity equations. So if we say continuity equations in cylindrical coordinate is given by this equation here. Now we are putting our constraint. Sorry, the constraint first is we are considering steady state flow, so this term is getting cancelled. Then we are considering here flow is totally in z directions only, so VR term is 0. Then no velocity, no flow in theta direction also, so this term B theta is also 0 actually. So flow is parallel to pipe wall, therefore VR and V theta are 0. So from here you are getting del Bz upon del Z term is equal to 0, or you can write this term would also be equal to 0 from fully developed flow in Z directions. Now axisymmetric flow, so theta is not the function of time and theta, so Bz is not function of t and theta. So steady state, so this del B upon del t term would be 0, and totally in function of r, because axisymmetric is not function, so Vz is totally a function of r only. So this is how you can calculate your gr is minus g sine theta actually, radial directions. So you will get this g theta is minus g cos theta, so g theta is given by this one only. So this is how your value of g would be calculated. Now you have r momentum balance. So if you write r momentum balance is given by this, and we can simplify that, and then you are calculating from here. This is steady state, this term will calculate 0. One dimensional flow only in z direction, so VR and V theta equal to 0. So this and this is also getting 0. VR you have already put 0 due to one dimensional flow in z direction, so this is 0, this is 0. V theta, there is no velocity in theta direction also, so one dimensional flow case, this is also 0. Del VR upon del Z is also 0 because VR is 0. So totally we end up is 0 equal to minus rho g sine theta minus del P upon del R. We can write del P upon del R equal to minus rho g sine theta. So we can integrate it for entire r, actually rho g sine theta r here. So we will calculate here rho g r sine theta, a function of z. It indicates that pressure is hydrostatically distributed at any particular cross section, and z component of pressure gradient. So del P upon del Z is not a function of r and theta. Now theta direction, so we can write here theta direction component rho del B theta upon, so this is the momentum balance theta direction, so all B theta terms are 0, VR terms are 0, so the everything here comes to be 0 except these pressure terms. So you got 0 equal to minus 1 upon r del P upon del theta plus rho g theta. So rho g theta is g cos theta. So P upon r equal to minus rho g sin theta equal to f2z. So you will get here the P equal to minus rho g r sin theta plus f2z. Now P equal to minus rho g y plus f2 sin theta. Now z direction momentum balance. So z direction momentum balance is given by these equations. So the steady state flow, so del upon del z is 0, VR and B theta are 0 due to one dimensional flow in z direction only. Del Bz upon del Z equal to 0 from continuity or fully doubled flow in z directions. Del Bz upon del theta is 0 axisymmetric flow. Del Z equal to 0 due to fully doubled flow in z direction or from continuity. So we end up with here the 0 equal to minus del P upon del Z plus mu 1 upon r del upon del r del Bz upon del r. So from here is 1 upon mu del P upon del Z equal to 1 upon r del upon del r del Bz upon del r. So this can be integrated from here, where del P upon del Z is minus delta P by L. So we will get expression for del B upon del Z equal to minus delta P by 2 mu L r plus C1 upon r. Then again integrating here, delta Vz equal to minus delta P for mu L r square plus C1 ln r plus C2. This is equation number 3. Now we have boundary conditions at r equal to 0, velocity equal to maximum at the center line velocity. So but this term is becoming infinite. So to make it finite, we are forcing that C1 must be equal to 0. So this first constant is 0. So your Vz expression is minus delta P for mu L r square plus C2. Now at r equal to plus minus r, Vz equal to 0, no slip boundary conditions. So we can substitute that. So r equal to equation number 3, 0 equal to delta P for mu L r square upon C2. So C2 comes out to be delta P r square upon 4 mu L. So from here we can get Vz equal to delta P r square upon 4 mu L 1 minus r square upon r square. So from here B max at r equal to 0 is delta P r square upon 4 mu L. Now shear stress again tau rz equal to mu del B upon del r. So tau rz upon mu is del Bz upon del r. So we can calculate from equation number 2 here is minus delta P upon 2 mu L r. So we can get delta tau rz equal to minus delta P upon 2 L into r. So this is the linear profile. Now we have volumetric flow rate Q equal to V dot dA. So this is the linear profile. Now we have volumetric flow rate Q equal to V dot dA. So this is the linear profile. Now we have volumetric flow rate Q equal to V dot dA. So this is the linear profile. Now we have volumetric flow rate Q equal to V dot dA. So this is the linear profile. Now we have volumetric flow rate Q equal to V dot dA. So this is the linear profile. Now we have volumetric flow rate Q equal to V dot dA. So this is the linear profile. Now we have volumetric flow rate Q equal to V dot dA. So this is the linear profile. Now we have volumetric flow rate Q equal to V dot dA. So this is the linear profile. Now we have volumetric flow rate Q equal to V dot dA. So this is the linear profile. Now we have volumetric flow rate Q equal to V dot dA. So this is the linear profile. Now we have volumetric flow rate Q equal to V So 0 to 2 pi, 0 to r, v r d theta. So this is velocity expression delta p r square for mu l minus 1 upon r square into r dr. So if we integrate that, we will get this one. Finally we will end up this, that q equal to pi r4 delta p 8 mu l is known as Poiseuille's law. Average velocity is q by a, so you already have q, then we have the area 0 to 2 pi, 0 to r dr d theta or pi r square. So for that, average velocity comes out to be r square delta p upon 8 mu l, which is half of maximum velocity. So the relation between maximum velocity and instantaneous velocity, Vz equal to Vmax bracket 1 minus r square upon r square. So this is all about the Newtonian fluid flow in circular tube. Thank you.